Salam and welcome everyone. So today we're going to be working on the question on the screen that says a sample of nitrogen gas of mass 3.12 grams at 23.0 degrees Celsius is allowed to expand reversibly and adiabatically. Remember, we have an expand reversibly and adiabatically in the question, and that tells us that we're going to be dealing with a reversible adiabatic expansion problem from 400 centimeter cube to 2.00 decimeter cube. What is the work done by the gas? So we're asked to solve for the work done by the gas. The first thing you have to note is this information right here. We're going to write out all of the parameters. So to solve this question, of course, we're going to write solution because we're starting to solve. We have the mass of gas that we're given to be 3.12 grams. We've got the initial temperature to be 23.0 degrees Celsius. We've got the initial volume to be 400 centimeter cube, and we've gotten the final volume to be, no, we've gotten, sorry, we have been given the final volume to be 2.00 decimeter cube. So 2.00 decimeter cubed. And we've also been told that we're going to use the molar heat capacity at constant volume for this particular question to be 20.81 joules per mole Kelvin. So we've given all of this information right here. And of course, we're told to solve for the work done. Now, the first thing you have to note is our temperature is given to us in degrees Celsius. We have to go from degrees Celsius to kelvins. That's how you solve any question in thermodynamics. So that would be 23.0 plus 273.15. So the T initial would just be 296.15 kelvins. So that is what we're going to be using in this question. Now, one thing I want you to note is this. For a reversible adiabatic expansion problem that involves the work done, we're going to be using the formula N times CV, comma M times change in temperature. So we are going to be using the number of moles. We're going to be using the molar heat capacity at constant volume, and we're going to be using change in temperature. But the issue here is that change in temperature requires us to subtract the initial temperature from the final temperature. But the question here is we're not given the final temperature, which means we have to solve for the final temperature. So that is basically the important thing. So before we can even do the work done, we have a lot more to do first. T final in an adiabatic reversible expansion has the formula T initial times V initial divided by V final raised to the power of 1 over C, where C is equal to the molar heat capacity at constant volume divided by R, the gas constant. So we've been given the molar heat capacity at constant volume, right? We know that to be 20.81 joule per mole Kelvin. And we know the gas constant is a constant. So that's going to be 8.3145. We can easily solve for the value of C. So C is now going to be 20.81 joule per mole Kelvin divided by 8.3145 joule per mole Kelvin. So of course you cancel out joules cancel out mole Kelvin. So C is now going to be equal 20.81 divided by 8.3145. We have that information to simply be putting that information in calculator. We're going to have 2.502. So that's the answer here. So that's basically what's going on here. Now you can think, oh, well, we have our initial volume, we have a final volume, we have our initial temperature. So initial temperature check, initial volume check, final volume check, and we have the value of C. Then we can just simply input all of this information. This is very true, but the issue with this is that we still have one more thing to fix. So let me write the value for C here quickly, 2.502. We have one issue to fix. If you notice our volume is not in the same unit. Our initial volume and our final volume are in completely different units. So you know that whenever you're dealing with calculation problems in chemistry, you have to make sure that the initial volume and the final volume, or the initial state and the final state, are always in the same unit, always have the same unit. So we would now go from centimeter cube to decimeter cube. You can either make sure that the initial volume and final volume are both in centimeter cube, or you can make sure the both of them are in decimeter cube. I am going to be making sure the both of them are in decimeter cube. So we're going to be going from 500 centimeter cube to whatever that value is in decimeter cube. So we have to note, we have to remember, I apologize, 1 decimeter cubed is the same thing as 1,000 centimeter cubed. Hence, 400 centimeter cubed is going to give you what value? So I'm going to be using the proportionality method to calculate this. I'm going to use the unknown x for us to determine it. So we have 400 centimeter cube dm cube is equal to 1000 centimeter cube X, right? So solving this, we're going to cancel out centimeter cube. Remember, we're trying to solve for 400 centimeter cube in decimeter cube. So we have to cancel this. And also, both units are in both sides of the equation. So that will be X equals 400 decimeter cube divided by 1000. So that's just going to be X equals 0.400 decimeter cubed. So our initial volume is going to be V initial is actually going to be 0.400 decimeter cube. And this is what we're going to be substituting in this particular equation. So yeah, that's basically it. Now we're ready to substitute and continue with our calculation. So I'm trying to erase this. I don't know what's up with the eraser today. Okay. So yeah, it's working now. So inputting our information, we have T final is now going to be T initial. We know that to be 296.15 kelvins. The V initial is 0.400 decimeter cube. The V final is 2.00 decimeter cube. We have 1 divided by the C value to be, the C value is 2.502. Yeah, that's basically it. So cancel decimeter cube, you end up with T final is equal to 296.15 kelvins. Now, this entire information I'm going to put in a calculator. If you don't know how to put in complex information in a calculator, start learning to do that. Start learning to plug in fractions and powers in your calculator, because that's how you can solve questions like this. You're not going to be doing the math in your head, especially if you're in a test. That's not even going to be easy for you to do, to be honest. So you actually do need a calculator. So this whole information, putting in my calculator, I'm going to get 0.52556. That's it. So the T final would end up becoming 155.645 kelvins. So that is basically how you get this done. This is basically how you solve this. So we've gotten the T final, and we know that in order for us to find the work done, which is actually what our question is, we have to have the T final. So rewriting the equation for work done. So adiabatic work done is equal to the number of moles times the molar heat capacity at constant volume times the change in temperature. We can solve for the change in temperature because we have T final and T initial. We know the value given to us for the molar heat capacity at constant volume, and we have the number of moles. Before we solve this one, let me quickly mention this. This is a question from a textbook, all right? I want you guys to note that we're not given the CVM value. It's possible for you to be given or to be using a different CVM value in your thermodynamics/physical chemistry class. So if you're using that, maybe your professor gave you a particular value to use, please use that. This value is actually correct. You can either use the resource section of your textbook. I use Google to find this one. So it's possible for you to be given 28 points, maybe 82 rather than 81. It's possible for you to be given 28 point something. Sorry, 20 point something. So just put that in mind that sometimes these values would vary, but that 20 points is going to remain the same. It's just whatever is after the decimal point, it is what can vary a little bit. So just put that in mind. But for this question, we're going to be using 20.81 joule per mole Kelvin. So next, we're told the number of moles times the change in temperature times the molar heat capacity at constant volume. We don't have the number of moles. We can solve for that, right? Because that's easy. We have the number of moles equals mass divided by molar mass. And we know that the mass of the nitrogen is 3.12 grams. So that would be 3.12 grams times the molar mass. And the molar mass of N2 gas is just 28.013 gram per mole. Now, note this. I'm not going to solve out the molar mass of nitrogen gas. By this point in time, this is like advanced chemistry, so you guys know how to do it already. If you want me to write that step by step, I think you can just easily Google it and you're going to find that the molar mass for nitrogen gas is 28.013 gram per mole. So yeah. So the number of moles, 3.12 grams divided by 28.013 grams. You cancel out grams. Gram per mole, you cancel out the grams. You have 3.12 divided by 28.013. And putting that in my calculator, I got 0.11138 mole. So this is actually the number of moles. So now we have the number of moles. We have all the other values. So we just have to substitute. So the adiabatic work done is actually 0.1138 mole, okay, times light capacity at constant volume. So that's going to be 20.81 joule per mole Kelvin. So that'll be 20.81 joule per mole Kelvin, okay, times change in temperature, which is just 155.645 kelvins minus the initial temperature, which is simply 296.15 Kelvin. So, yeah, the adiabatic work done is now going to be 0.1138 um mole, okay, times, I'm rewriting it, 20.81 joule per mole Kelvin times 155.645 minus 296.15 Kelvin is the same thing as negative 140.505 kelvins. So of course you cancel out the mole, cancel out the mole, cancel out the Kelvin, cancel out the Kelvin. You cannot input all of this information in your calculator to be 0.1138 times 20.81 joules times negative 140.505 would end up giving you negative 325.665 joules. Now, if you go back to our question, you can see that we have the mass in 3 sig figs. We have 400 centimeter cubed in 3 sig figs and 2.00 in 3 sig figs. The lowest number of significant figures in this question is in 3 significant figures. Is in 3 sig figs, right? So what that is telling you is that we have to put our final answer in 3 sig figs. So what we end up with our adiabatic work done is going to be negative 326 joules. And this is the adiabatic work done for this question in 3 sig figs. If you have any questions, please put in the comment sections. Sorry. If you have any question, please put it in the comment section. If you have any concerns or suggestions, also put it in the comment sections. I help students who are trying to succeed in all their STEM related courses to succeed. So if you would like to book a session, or if you would like to talk about how you can improve academically, or if you would want just tutoring or mentoring services, you can email me at shahabitutoring@gmail.com. I help students who are trying to succeed in your academic life, succeed and be the best version of themselves with regards to academia. So if you have any questions, or if you have any interest in my services, please email me at shahabitutoring@gmail.com. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.